let's be real. The climate crisis is one of the biggest challenges we face, and that means we need some seriously innovative solutions for capturing carbon. Today, we're diving into a really cool new frontier, using electrochemistry to literally pull CO2 out of the air and water.
So, just how big is the problem? Well, let's put a number on it. Back in 2022, the CO2 in our atmosphere hit 421 parts per million. That's over 50% higher than it was before the Industrial Revolution. It's a number that really tells you, yeah, we need to act fast. Now, what if I told you a potential solution could be that simple? It sounds almost too good to be true, right? But what if the key to powerful carbon capture is just clever chemistry, powered by something as basic as electricity? That's the big idea we're going to unpack. All right, here's our game plan. First, we'll cover why we need to do better than the tech we have now. Then, we'll get into the details of this elegant pH swing idea. We'll compare two different ways to do it, organic versus inorganic, and see where they could be used, from factories to the open ocean. And finally, we'll look at the hurdles and what the future holds. Okay, so first up, why even bother with something new? I mean, we already have carbon capture, right? Well, yeah, but the current methods have some pretty big drawbacks, and that's exactly why scientists are looking for a better way. And this slide really nails the difference. Think of conventional capture as brute force. You use these volatile chemicals, and then you have to blast them with tons of heat to get the CO2 back out. It's just incredibly energy hungry. But the electrochemical approach, it's way more finessed. It runs at a constant, low temperature, uses more stable materials, and could be a whole lot more energy efficient. And that brings us to the star of the show today, the electrochemical pH swing. Honestly, the best way to think about this is like a rechargeable chemical sponge, a sponge that you can turn on and off with electricity. So here's the magic trick. The amount of CO2 that water can hold is totally dependent on its pH. If you make the water alkaline, a high pH, it gets really thirsty for CO2, just soaks it right up. But if you make it acidic, a low pH, it lets all of that CO2 go. And the pH swing process uses electricity to just flip that switch back and forth. Let's walk through it. Step 1. Charge. You zap the system with electricity, which makes the solution alkaline. Step 2. Absorb. Now that alkaline solution is like a super absorbent sponge, you expose it to CO2 from, say, a smokestack, and it just vacuums it up. And finally, step 3. Release. You reverse the electrical current, the solution turns acidic, and it can't hold on to the CO2 anymore. It literally squeezes it out as a pure, concentrated stream. Now, there isn't just one way to build the sponge. Researchers are actually exploring two totally different paths based on two different families of materials, organic and inorganic. So how do you actually build this thing? This is where the chemistry gets really cool. The sponge isn't a physical thing. It's a special chemical called a redox active material. All that really means is that it's a molecule you can control with electricity, telling it to gain or lose electrons. And that's what drives the whole pH change. Let's see how. Okay, path number 1 uses these special organic molecules that you just dissolve in water. They're like these tiny free-floating agents, and when you apply electricity, they're the ones that do all the work of changing the pH. A perfect case study for this is a molecule called 1AP. On the one hand, its performance is off the charts, super efficient. But here's the catch. It's not very stable. Over time, it just starts to break down, which is a huge problem, especially right where you need it to work, at the interface between the liquid and the gas. But just how efficient are we talking? Well, the 1AP system managed to capture up to 1.25 moles of CO2 for every single mole of electrons it used. In this field, that is an absolutely fantastic number. It shows you the massive potential here. If, and it's a big if, they can solve that stability problem. So to try and fix that stability issue, researchers looked at another molecule, neutral red. And its secret weapon? It's totally stable even when there's oxygen around. And that, right there, is a game changer. It means you can use it for direct air capture, or DAC, pulling CO2 straight out of the air all around us.
All right, let's look at the second path, which is a completely different strategy. Instead of dissolving molecules in the water, the electrodes themselves are the active material. The pH swing reaction happens right on the solid surface of the electrode.
A great example of this is manganese oxide. When you charge this electrode, it literally pulls protons, hydrogen ions, out of the water and stuffs them into its own solid structure. This process, called intercalation, makes the water around it alkaline, which is perfect for capturing CO2 from something like a factory's flue gas. The only problem? It doesn't work in saltwater, because all the sodium ions just get in the way and mess things up.
So this table gives us a great side-by-side comparison. You can really see the trade-offs. For the organics, one op is a performance beast, but it's unstable. Neutral red is stable enough for air capture, but it's a bit slow. Then on the inorganic side, manganese oxide is great for flue gas, but it hates salt. And bismuth, it works in seawater, which is amazing, but it's also kind of sluggish. So right now, there's no single silver bullet.
But what's so cool about having all these different approaches is that it means we could develop customized solutions for different problems. One system for industrial smokestacks, another for the open air, and maybe another one for the biggest carbon sink on the planet, our oceans.
And that brings us to the most ambitious idea of all. Our oceans have soaked up a massive amount of our CO2 emissions, which is making them more acidic. This quote from the paper lays it out. If we can pull that dissolved carbon out of the seawater, the ocean will naturally suck more CO2 out of the atmosphere to get back to equilibrium. The end result? A net reduction of CO2 in the air.
This is where those bismuth electrodes make their grand entrance. See, unlike manganese oxide, the bismuth system has a clever workaround. It uses the chloride ions from the salt and seawater to split water and drive the pH swing. It neatly sidesteps that whole sodium interference problem, making it a fantastic candidate for direct ocean capture. Now, this all sounds pretty incredible, right? But we have to be realistic. This is still cutting-edge science. There are some major hurdles to clear before we can roll these things out at the massive scale we need to actually make a dent in climate change. What this all boils down to is a set of really tough engineering problems. For the organic stuff, it's all about making molecules that don't fall apart. For the inorganic electrodes, it's about making them big enough and stopping them from getting gunked up with minerals from the water, a process called fouling. And for every single system, they've got to be more energy efficient and last a long, long time to make any economic sense. The truth is, the story of pH-Swing electrochemical carbon capture is really just getting started. The work we've seen so far has proven that the concept is powerful and it's flexible. It's basically laid the groundwork for the next big wave of innovation. And that leaves us with the billion-dollar question. The materials we've looked at today are just the beginning. The real challenge now is for scientists and engineers to keep exploring, to fine-tune, and to invent that next-generation material or system that finally turns this amazing promise into a real-world, large-scale, sustainable solution.